Well, so we'll be looking today at complex reflection groups, characters for them, and try to compute the probability measures there. So it's going to be very interesting, lots of roots of unity with respect to what we learned last time about the symmetry group. So it's going to be a bit the same thing, but with roots of unity thrown in and sums and all that. And it's going to be also a bit tough. I mean, that's a bit research level, but I'm trying here to avoid as far as possible research, and that's why we left things with representations for later. But now it's time. I mean, when we're having fun with combinatorics, you get to the things which are advanced. But it's gonna be nice and unpleasant. So this is the presentation: complex reflection and Bessel laws. As you can see, Bessel, that's a scary thing, and it's going to be scary at some point. So let's start with some algebra. So the reflection groups that we're interested in called HNS. So they depend on n, the size of the matrices, and S is the order of the roots of unity. Can be finite or infinite. So infinite means that nothing happens. It's an arbitrary element of the unit circle. So I denote by ZS the roots of unity of order S. So HNS is the group of n matrices with entries in ZS and 0, such that on each row, each column there is exactly one on 0 entry. Okay, so it's like permutation matrices but decorated with roots of unity somehow. So this is one, of course, from the symmetry group. S is 2, that's the hyperoctahedral group. I mean, plus minus ones like permutations. These are exactly the hyperoctahedral transformations. At S 3, 4, 5, etc. Well, it's no longer orthogonal here. It's unitary, so it's a certain finite group of unitary matrices. And that S is infinity. So here we have matrices like permutation ones. Okay, so on each row, each column, just one non-zero entry, but that it can be on a unit circle. So this is unitary, of course, but it's infinite this time. So what's the theory about all these things? Let me tell you a bit without proofs. I mean, these are interesting things. It's good to know them. If you're interested, you can learn them later. So first of all, well, we know that the matrices, it's somehow, HNS is Sn decorated by roots of unity. And in algebra, this means that you have a Riesz product decomposition, ZS, and then this sign is called the Riesz product Sn. So that's, well, that's something that we know. Let's say basically it's an algebraic formulation for this thing that you can see on the matrices. Now, another thing now, which is deep, really complicated, is that the complex reflection groups, which are irreducible in a certain technical sense, are exactly these guys with one more parameter added, coming from the fact that the determinants should have to the power d is 1. ZD, I remind you, that's the roots of unity, and of order d. And that's all. I mean, this is the series depending on 3 parameters NSD, and then you have exceptional examples which are classified by Shepard and Todds. In the 70s, I think, there are 34 of them. So big results, of course. Very complicated, the proof. Now, one more theorem, which is also tough, is that these corner groups are easy. These groups, sorry, are easy in the sense that, well, this goes back to Brouwer. So what Brouwer discovered, it's about orthogonal unitary groups, but also applied to these finite groups like symmetric and the others, is that if you look at the fundamental representation, let's call it pi, and some hot tensor powers of that, well, the main problem is to decompose somehow these tensor powers, and more precisely to compute these spaces of intertwiners, the so-called Tanakian category. It's very important. That's the main thing to be done with the group. We'll get to this later when doing representations. And now this Tanakian category, well, these are finite dimensional spaces. So the idea would be to find a basis for that, which is very simple. And the simplest case is that when we have a basis spanned by set theoretic partitions, these are the simplest combinatorial objects. And that's the Brouwer result. It's so-called Brouwer algebra. And well, these groups now going back to reflection. So these groups HNS are easy. So for those who know with Brouwer everything, here in the Brouwer diagrams are partitions such that this condition is satisfied. Number of whites is number of blacks, modulo S, the whited count in each block. Well, white stands for pi and black stands for pi bar. For those who know, we'll get into this later. But anyway, that's to be known. And well, let's go back to a previous slide. These guys are not easy actually, HS and E. So that's why easiness is something important is behind everything that we're doing. So that's why we won't add this parameter D. We'll keep the we'll stick to HNS. These are the easy and simple things. So finally, after all these deep things, so what to do? Shall we get into this algebra things, risk product, stuff like that, or into Shepard and Todd's terrible too, or this is in a things which is terrible too? And the answer is no. I have actually something simpler and more fun and also very useful to be done. Compute the laws of characters and also truncated characters. Why? Because we've seen last time at S is 1 where I have the symmetric group, things are not complicated. I mean, you just use the inclusion-exclusion principle and you get plus 1 of 1 for the character and plus 1 of t for truncated characters when it goes to infinity. So very, very nice results. And these are somehow more interesting. They come before these things, which are very, very advanced, all the others. So that's something definitely to be done. It's not going to be hard, and we'll get to interesting calculus, roots of unity, all that, and it's deep. It's a very good introduction to the subject. We're talking today about these reflection groups, those which are easy somehow, that parameter D, and we're trying to do this thing, computation of the characters. That's the good problem to start with, introduction to the subject. So let's start with the S is 2. So we know for S is 1 is plus 1, S is 2 hyperoctahedral group. That's something that we know. It's at the same time a symmetric group of the hypercube or the n-coordinate axis. Right, rotating the hypercube is the same as rotating the coordinate axis. And the matrix form, these are permutation line matrices, but plus minus 1 non-zero entries. And the general theory is that you have this risk product decomposition. The reflections to groups are Shepard and Todd. Well, the determinant can be plus minus 1, so you only have a 1 subgroup which is intersecting with SON. And also easiness, that condition would modulate all that when S is 2 is very simple, just the partition of those having given blocks. So it's something very basic, the hyperoctahedral group. Now, well, the computation can be done with the inclusion-exclusion principle. I mean, as for SN, but you just have to decorate things with signs. So it's, yeah, definitely can be done, and you get this kind of thing here. So the law, once again, when n goes to infinity, it's a bit like plus 1 style, starting with the exponential minus t. Now I have this base here. So first of all, because you have signs, it's supported by z now. You see these matrices. We're looking at the trace of matrices. 0, 1, minus 1 permutation like, so the trace is an integer, no longer positive. So that's why it's supported by z, and well, it's also centered. And when we get this function here, if you do the computations, which is not that bad, and actually the good news is that this is a known function in analysis. That's the function, it's the Bessel function of the first kind. So very interesting. So finding the formula, if you know some analysis, Bessel functions, that's all. It's called the Bessel law because of this Bessel function. So the truncated character law, it's exponential minus t, and then just the probability measure having this density of t over 2. Very simple, finally. Now, what can we say about these Bessel laws? Well, a bit analogy with Poisson laws. They have a semi-group property, and also there are compound Poisson laws in the sense that they appear as laws of differences of Poisson variables which are free. So to do this exactly as for SN, you compute the Fourier transform of this beast here, the Bessel function, and you get all this. Now let's try a bit to understand some probability. Now you see we're getting now into advanced probability. So let's try a bit to understand this Bessel laws, and also at the same time to construct their generalizations, because this was about HN. We want to look at HNS that's arbitrary. So let's do some probability, okay, for a few slides, and then we'll go back to complex reflections. So as I told you before, yeah, these are compound Poisson laws. So that's the theorem, the general theorem, the compound Poisson limit theorem, says that you take a compactly supported measure on R, having mass T. Why T? T is our truncation parameter. It gets better to view this way as the mass of the measure. And then you do this thing. It's exactly as the Poisson limiting theorem, but instead of a Dirac at 1 here times T, put an arbitrary measure mass T. So this limit converges, and the measure is called compound Poisson law. And now, importantly, equivalently, if you have a discrete measure like this, you get the compound Poisson law is given by the law of the sum of these guys. So alpha I must be independent, and following the laws Poisson Ti. So you see the Ti's go here, and the Zi go here. It gets inverted somehow. So that's the general result. So it generalizes the Poisson limit theorem. Now, as many examples. Well, let's plug in the. So you see, let's go back here. So new, well, actually, it can be complex. There is a typo here. Well, the simplest complex measures are the measures on the roots of unity, right? And we can multiply by t. So these are the simplest compound Poisson laws, depending on parameter t and s. Let's call that higher Bessel laws. So we are the s here. So what does this mean? Well, by definition, this means the measure appears like this, compound Poisson limiting theorem. Reference, you have this formula. So finally, it's just you take Poisson T variables independent, S of them, and you multiply by roots of unity, and you sum. That's all. So that comes from the formula here. So these are called Bessel laws. Example, S is 1 is Poisson, S is 2 is the Bessel from the hyperoctahedral group. S34, we obtain certain discrete measures in a complex plane, and no surprise, this will be the measure for HNS. I'll show it in a second. For S is infinity, we obtain certain measure, let's call them BT with capital B. I'm using here a bit of non-standard notation, so this comes actually from advanced probability and free probability. It's customary to put letters like this, P and B for real measures, and capital letter for their complex analogs, and then use the Greek letters for free analogs. So you have, when you do like probability and free probability and all that, you need notations for all these measures and notations. So I'm using this kind of notations. Now, what can be said in general? Well, everything comes from Fourier when you do probability. So yeah, that's your Fourier transform, which is actually pretty obvious from this interpretation of the Bessel laws with the sum of Poisson's independent multiplied by roots of unity. So that's the Fourier of each Poisson, and multiply the roots of unity, get here to the exponents, and finally multiply by RT. Okay. And then they form a convolution semigroup when S is fixed with respect to T. Once again, it's clear because log Fourier is linear in T. So, very good. So I have this theory now. So what's left to prove is that, well, let's go back to the reflection group. So no surprise, that's a slide we already had before, so it's a reminder. So this is the HNS, the group of permutation like matrices with entries here. It generalizes everything. And now, no surprise, the laws of characters are these higher Bessel laws that we introduced. Once again, inclusion exclusion as for Sn and for Hn, but this time the permutations must be decorated by signs. Yes. And this is good. I mean, that's a final theorem. It unifies everything that I said so far. So this was pretty much it. Now, the problem is now, can we get beyond this? I mean, let's do things more complicated. And the actual idea would be to look at general reflection groups, adding this parameter coming from the determinant. But few computations there which are actually not really done. It's a bit of folklore what I'm saying here, recent folklore from the no 20, no end of 20th century actually, no, from the zeros, yeah, from the zeros and a bit from the tens. It's well, I'm not interesting at the same laws. So the fluctuations, that's a very interesting problem in understanding the fluctuations coming from the determinants. Now, another type of extensions, which is perhaps even more interesting, is sticking with these HNS, which are the ones that are easy somehow, but looking at the fluctuations of the characters, the truncated characters, or by smaller variables. For instance, the characters have this natural generalization by Yakunisha Shakani. Instead of taking trace of G, take trace of G to the K. K is in M. And well, very interesting questions here. And once again, it's a bit folklore. And these are well understood for the symmetry group, of course, and for the hyperoctahedral group. These things have been worked out, but in general, not really, and especially the fluctuations. So there's still research going on. So this combined with this, that's somehow what research in the area is about. So still many open problems, and as you can see, it's not very complicated. I mean, inclusion, exclusion, all that, but all the time we skip the details. Actually, I told you we did a computation in the beginning long ago with inclusion, exclusion, and then I'm telling you all the time that comes by extending all that. And these last extensions that we did today are quite technical. They actually take a few pages. I mean, it's just straightforward, but well, you have to do it. Takes a few pages. Lots of roots of unity summing there, and so that's why it's a bit research level. Things are not really well understood here. So that's what research is about. These complex reflection groups from probabilistic point of view to understand things. Very useful. And if you're interested, you can get to the research published papers very quickly after you learn a bit. So very nice subjects. Okay, so I think for the next two lectures there we'll go to compact groups now, Y and UN, and there you can't do inclusion, exclusion anymore. We have to go into this heavy representation theory, things like Peter White's theory of that, easiness, Brouwer, Tanaka. So we'll talk about all this, and also about integration in general and the Weingarten formula once again. Very modern stuff and interesting. So see you soon.